Can you see the screen?
Yes, ma'am.
Okay. As discussed yesterday, we have completed the design of continuous beam, that is the second unit. And now we will start with the next point from third unit, that is design for shear. Design for torsion. Design for shear, the A part from third unit we have already completed earlier. Let us come to the part 2 of unit 3, in which there are again two points. First is design for torsion, in which you need to understand how the RC member behaves under torsion, what are the torsional shear stresses developed, why it is required for the torsional design for torsional reinforcement, and what are the provisions given by Indian Standard Code for the design of RC member which is subjected to torsion. The next part is the concept and type of bond development mechanism, and bond failure. This part is actually more related with the slabs. So when we start design of slab, that is your fourth unit, then we will focus on the bond, because right now explaining you the theoretical part of bond, and then the actual problem we will consider when we design the slab, that becomes difficult for you to understand. So when we will start fourth unit, we will we will focus again on the concept of bond. So let us start with the first part, that is concept of torsion. Torsion is the another important force which causes the major action along with the other major structural actions like axial force, shear force, and bending moment. Okay, so if you consider any particular member, either it may be subjected to axial force or it may be subjected to shear force and bending moment. Normally, when there is a bending moment, there will be a shear force. So these two forces are associated with each other. So depending upon how the load is acting on a member, the forces developed in the member changes. So along with these important actions, that is axial force, shear force, and bending moment, the fourth major structural action is the torsion. Now, the torsion may occur due to the eccentric loading, which is not lying in the bending plane of any particular member, or it may be developed or may be transferred due to the transfer of rotation between interconnected members. For example, suppose there are two members, two beams are there, and these are connected with each other at one certain point, and because of the bending of one particular beam, the torsion may be developed to the another beam, may get developed in the another beam. So depending upon the compatibility of the interconnections between the members, the torsion may get transferred or may get developed due to the action of the another connected member. So depending upon the type of the action, the torsion is classified into two categories. First is the equilibrium torsion and second is compatibility torsion. Let us understand now both these types one by one. Equilibrium torsion is actually a torsion, a type of a torsion, which is developed in any particular member due to the action of the eccentric loading. So if you consider this particular structure in which there are two columns and there is one beam, and to this particular beam, a roof is connected or the roof is resting on this beam, and this is a cantilever roof. Okay, so you can imagine the same diagram with the cantilever slab or the balcony which you are actually considering in your G+2 plan of your term work. Okay, so or just imagine a balcony which may be present in your current existing house. Okay, now this is a cantilever shell roof in this particular exam. So you can consider a cantilever slab which is normally considered or which is there in case of the balconies. So whatever the load acting on this particular roof, because of that load, there will be a torsion developed in this beam. See, this is your beam. All of you, can you see the pointer which I'm moving here on the screen? Students?
Yes, ma'am.
So can you see my pointer?
Yes, ma'am.
Yes, ma'am.
Okay, okay. So the free body diagram of the same beam is drawn over here. So whatever is the load acting on this beam, or whatever the load coming from this roof, is transferred to this particular beam. So that load is shown in a vertical direction over here. So because of this vertical loading, the beam may bend like this. Okay, this is the shape after bending. So that bending moment is shown here at the supports, or at the end of the beam. But because of this cantilevered action of a slab, whatever the load acting on this roof, there will be one moment which is acting like this, and that moment is causing actually the torsion. So it is shown in this fashion. This particular arrow is showing us the total torsion, or which is also called as a torque. Okay, so this particular torsion is called as the equilibrium torsion, which is developed because of the eccentricity of the load. The load is not along the axis of the beam, it is somewhere far away from the axis of the beam, and because of that eccentric loading, a moment is developed, that is your twisting moment or torsional moment, or simply torque. Okay, so I think the concept of equilibrium torsion is very clear to you. So the same is written here. In equilibrium torsion, the torsion is induced by an eccentric loading with respect to the shear center of any cross section, and equilibrium conditions alone suffice in determining the twisting moment. So what is the equilibrium condition? Summation of moment at any particular point must be zero. So based on that, we take a moment and we find out what is the value of the moment acting on this beam. Okay, so this is the bending moment, whereas this is the twisting moment. Now you can just hold a pen or a pencil in your hand, and you can simply apply a equal and opposite moment at both the ends. What happens? Your pen or pencil will get twisted. Okay, so twisting action is there, and you can just imagine that these forces we are applying at the end of the pen. So this is the diagram of the twisting moment. Okay, so how it varies along the length of the beam, you can imagine quickly. So this is about equilibrium torsion, the first type. Second type is the compatibility torsion. Now consider this example. This is actually showing one frame or a part of a frame in which there are some primary beams. This is my primary beam, okay, which is resting directly on the column. This is the another primary beam. So ABC is one primary beam, EDF is the another primary beam. This is also a primary beam, CF and AE, because these are directly resting on the column. Whereas if you consider a beam BD, which is resting on beam ABC and EDF. Okay, so this is my secondary beam. So my secondary beam has a connection with this primary beam at joint B as well as at joint D. So whenever there is a load acting on ABC, this particular beam, the beam is going to bend because of the external loading. Okay, so because of that bending at this interconnection, there will be some twisting developed in this beam BD. That twisting is called as compatibility torsion. And why this twisting takes place? Because at the joint, the each and every member will try to make or develop an equilibrium. We want to achieve equilibrium, right? And to avoid the deformation, whatever is developed due to the bending of beam AB, that will be tried to compensate by developing the torsion in member BD. Okay, to achieve equilibrium at this particular joint B. Okay, so such type of torsion is called as compatibility torsion, which is developed due to the deformation of one particular member in the second member. The torsion is developed in the second member because of the deformation of the first member, because of the interconnectivity between these two members. Okay, so compatibility torsion and equilibrium torsion, both these torsions we do not consider into the design. Or what IS code suggests is that where torsion can be eliminated by releasing redundant restraints, no specific design for torsion is necessary, provided torsional stiffness is neglected in the calculation of internal forces. So in this case, that is most of the time, as per the IS 456, the compatibility torsion which is developed due to this interconnection of the member, that is normally neglected. Okay, because these can be released, these can be eliminated by releasing the redundant restraint. So for what we have to design, we have to design for the equilibrium torsion. So whenever there is a development of torsion due to the equilibrium condition or due to the eccentricity of the loading, we have to design a particular member for that torsional force only. Okay, so this is about the torsion. So it is now very clear to all of you that whenever you, in your term work, when you finalize your plan and when you show the balcony is nothing but your cantilever slab, or whenever you show a porch attached to any particular beam which is resting on a beam, because of that porch or because of the balcony which is a cantilever slab, the torsion will be developed in a beam, and that beam should be designed for this torsional moment. Okay, now all of you have already learned about the design of rectangular section, singly reinforced beam. Okay, now how the design of a beam which is subjected to torsion differs with respect to the design of singly reinforced beam, that we will study now. Okay, so is it clear the concept of equilibrium torsion and compatibility torsion?
It means that we are never going to design secondary beam.
Huh? I didn't
We
understand your
asking.
problem.
That means we never have to design secondary beam, no?
No, no, no. You have to design the secondary beam, but in the design of secondary beam, you need not to consider the torsion. Okay, there will be secondary beam in your plan. Definitely, there will be secondary beam. Okay, but when you design the secondary beam, you need not to consider effect of torsion in this particular beam. That is what IS 456 says. Is it clear?
And then how come it is compensated?
It is compensated by the deformation at this joint B, which is called as compatibility. You might have learned about the compatibility equation also na, in MOS 2. MOS 2. Who is talking?
Myself, Omkar.
Omkar. Huh. So you must have learned about the compatibility equations, compatibility conditions, and by considering compatibility condition, normally if your determinate beam sorry, indeterminate beam is there, to solve the indeterminate beam, we require the compatibility equations also. So those compatibility equations we
Yes,
consider
ma'am, that K
huh,
and all that.
at the joint, and at there only these deformations get compensated. So whatever the torsion developed because of the interconnection, that torsion is very, very small normally, and that we can neglect in the design. That is what IS
Okay.
specifies. But in case of equilibrium torsion, the amount of torsion developed on the beam is sufficiently large so that we need to consider its effect in the design. And hence, such beams are also designed for considering the effect of twisting moment. Okay? Is it clear now, Omkar?
Yes, ma'am. Yes, ma'am.
All right. So how the member behaves under torsion? So if you consider this is a cantilever beam and it is subjected to say a twisting action over here, it will twist like this. Okay, so equal and opposite action will be there at both the ends and it will entirely twist. Now when it twists, what happens on the surface? Because of this twisting moment, all around the surface of a beam, the shear stresses get developed. You can see here, this is along the surface of the member. So along the surface of the member, the diagonal cracks get developed because of the shear stresses developed in the beam due to torsional effect. So obviously you have already learned about the shear design. So that shear design we need to uh, change little bit when a torsion is acting on a beam. So when we design any particular beam which is subjected to all the three actions, three means shear force, bending moment and torsion or twisting moment. When all these three forces are acting on any particular beam, we need to make certain changes in the design. Now how these changes are made? So if you recall the design steps for design of beam, let us consider a simple example, design of a rectangular section. Which we have to design like a singly reinforced beam. In this, we consider the force, one force, that is the bending moment, separately. And for to resist that bending moment, we provide the tension steel in the tension zone. Okay. And then the second force is shear force, in which to resist that shear forces, we provide the stirrups, which are along the face of the member. Okay. So by providing tension steel and stirrups, we actually considering the resistance shown by the member to the bending moment as well as shear force. Now the third force get entered, that is the torsion. Now torsion, for torsion, we do not consider any separate action. So we do not consider any separate steel which is located at some separate location, but its effect is considered, or it is combined along with bending moment and shear force. So whatever the bending moment we calculate, or whatever the shear force resistance we calculate, those formulas are changed by including the torsional moment. Okay. And again, the concept remains same. We design the we provide the tension reinforcement now, but not only for the bending moment, but to take care of the torsion moment also. So obviously your reinforcement in the tension zone will little bit increase, okay, to take into account the effect of torsion. Similarly, when we design the beam for the shear force, along with shear force, we have to consider the stresses, shear stresses developed due to the torsional action or twisting action. So your shear force will get added or will get increased because of this torsion action or twisting action. And obviously for that combined effect of shear force, we have to design, or we have to provide the stirrups. Okay, is it clear? So once you note down or you observe the design steps for design of torsion or design of beam subjected to torsion, you will quickly understand how the design changes. Okay, so let us come to the design steps now. The first step is we have to calculate ultimate bending moment, shear force, and ultimate twisting moment. In case if you have provided any porch or any cantilever slab in your term work plan or in your building, because of the load acting on that cantilever slab, whatever the moment developed at the beam, that you have to calculate as ultimate twisting moment. Okay, so that is TU. Now the next step, select a suitable size of the beam. So the usual step, whatever we have learned in the design of rectangular beam, that is we have to decide the width of the beam, then we have to decide depth of the beam, and we have to decide the span of the beam. Afterwards, the third step is we have to calculate the equivalent bending moment. As just now I have explained, we do not consider the third force, this TU, as a third force acting on a member, but we consider its effect into bending moment and shear force. So when we design any particular beam subjected to torsion, we design it for bending moment and shear force only, but the moment value, bending moment value and shear force values are considered along with the effect of twisting moment. So these are called as equivalent bending moment or equivalent shear force. We do not call it as simply as a bending moment, because that bending moment has the effect of bending action only. In case of equivalent bending moment, the total moment has both the actions. One is the bending action and second is the twisting action. Okay, so it is called as an equivalent bending moment, which is denoted by ME1, which is calculated as mu plus mt, where mu is your ultimate bending moment and mt is your ultimate twisting moment, which is calculated based on tu value. Tu is the torque. Okay, so mt is calculated by using this formula, tu into bracket 1 plus d upon b divided by 1.7. Now this formula is given in IS 456. So let me open IS 456. All of you are also requested to open IS 456, page number 75. I hope everybody is sitting along with IS code. Okay. So if you open page number 74, you will find out one clause, clause number 41, limit state of collapse for torsion. Okay, I'm reading this particular paragraph because whatever we have just now discussed about the equilibrium torsion and compatibility torsion, the concept regarding that is a little bit given over here. So I'm just reading it. In structures where the torsion is required to maintain equilibrium, member shall be designed for torsion in accordance with 41.2, 3 and 4. These are the clauses. That is when a torsion is required to maintain the equilibrium. That is the equilibrium torsion. For that, we have to design the beam considering its effect in the beam. However, for such indeterminate structures where torsion can be eliminated by releasing redundant restraints, no specific design for torsion is necessary. Okay. However, for indeterminate structures, so indeterminate structures, when we consider the different joints and where we develop the compatibility equations, and because of the compatibility action, when the torsion is developed, that torsion need not be designed. No specific design for torsion is necessary. It is clearly mentioned in the IS code here, provided torsional stiffness is neglected in the calculation of internal forces. Adequate control of any torsional cracking is provided by shear reinforcement. So as we discussed, so because of the twisting action, the shear stresses are developed along the surface of the beam, and that is because of that the diagonal cracks get developed in the beam, and those diagonal cracks can be controlled, which are because of the torsion effect or twisting effect, by providing sufficient shear reinforcement. So whatever the shear reinforcement design we have already learned, the same concept we have to use, only instead of VU we need to calculate now the equivalent shear force. Okay, so one more note is given here, I'm just reading that also. The approach to design in this clause is as follows. Torsional reinforcement is not calculated separately from that required for bending and shear. Instead, the total longitudinal reinforcement is determined for a fictitious bending moment, which is a function of actual bending moment and torsion. Similarly, web reinforcement, that is your stirrups, is determined for a fictitious shear, which is a function of actual shear and torsion. So whatever I have explained is as per this statement. Okay, we calculate the equivalent bending moment, which has effect of both bending moment and torsion moment, and we calculate the equivalent shear force, which has the effect of both actual shear and torsion. Okay, so here is the formula for our longitudinal reinforcement. See here, this is the clause. Reinforcement for torsion when required shall consist of longitudinal and transverse reinforcement. Longitudinal reinforcement, the longitudinal reinforcement shall be designed to resist an equivalent bending moment ME1 given by ME1 is equal to MU plus MT, where MU is the bending moment at the cross section and MT is given as TU into bracket 1 plus D upon B divided by 1.7. What is TU? TU is the torsional moment. I will show here. TU is the torsional moment, D is the overall depth of the beam, and B is the breadth of the beam. Okay, so this formula is from IS code. You need not to mug up this formula. It is there in the code IS 456 page number 75. Okay, so once we calculate MT by using this formula, we have to compare this value with the actual moment acting on a member or on a beam. MT, if this MT is greater than MU, we need to calculate the ME2. It means whatever is this moment developed because of the twisting moment or MT value, if that is greater than the MU, it means the effect of torsion is more or large as compared to the bending moment. And then in that case, we need to provide some additional reinforcement to take care or to resist this particular moment. Okay, so that additional moment is calculated by this formula. Me2 is equal to MT minus Mu. Okay, so this is again as per this clause which we have just now discussed. So I will go back here in the code and I will show you that clause again. What the clause says. See here. If the numerical value of MT as defined in 41.4.2, that is this clause, 41.4.2, this clause, okay, exceeds the numerical value of the moment Mu, longitudinal reinforcement shall be provided on the flexural compression face, such that the beam can also withstand an equivalent Me2 given by Me2 is equal to MT minus Mu, The moment Me2 being taken as acting in the opposite sense to the moment Mu. Okay, so Me2 is calculated when Mt is greater than Mu, and to resist this Me2 moment, we need to provide some additional reinforcement in the compression phase. So whatever the tension reinforcement we provide in the tension zone of the beam, that will be calculated for this Me1 value. Okay, and for Me2 additional movement or the equivalent movement, for that we provide the additional reinforcement in the compression zone. Okay, that is in the top portion of the beam. Are you getting this? So we need to calculate now two area of the steels, one which will resist Me1 and second which will resist Me2. The same is given in the next slide here. So if Mt1 is greater than Mu, we calculate Me2, and then we calculate the longitudinal reinforcement on both the sides. One is on the tension side. The formula is same, whatever we have learned for design of rectangular singly reinforced beam. Okay, the same formula is there. Only instead of Mu, we have to put now the equivalent bend, equivalent moment, Me1. And by considering Me1, we whatever the area of steel we get, that we have to provide in tension side. If there is Me2, now Me2 will be there only if Mt is coming greater than Mu. If your Mt is coming less than Mu, then you need to show this calculation only. There is no need to provide the steel in compression side. Okay, but if there is Me2, then we need to calculate the area of the steel in compression side, which is based on the Me2 moment. Okay, is it clear up to this step, everybody? Students?
Yes, ma'am.
Okay, so the initial steps in the design of beam are exactly the same what we have learned earlier. Only the thing, Mu, along with Mu, we have to calculate the equivalent moment, and for that equivalent moment, if two equivalent moments exist, Me1, Me2, we have to do the calculation of area of steel separately for tension and compression side. And the next step is directly the design for shear. Now in the design for shear, whatever the Vu value we calculated earlier, that is the maximum shear force acting on a beam, that is calculated now in addition with the effect of torsion. So that Vu is already with us, plus this 1.6 Tu upon B, this factor we need to add to find out the equivalent shear force. Again, this formula is there in the IS code, IS 456. So if I will go to IS 456, clause number 41.3.1, equivalent shear is calculated by using this formula. Okay, Vu plus 1.6 Tu upon B. By using this formula, we calculate the equivalent shear. And for this equivalent shear, we have to follow the same process for design of shear, whatever we have followed earlier. Okay, so only at two stages our formula changes. One is instead of Vu, we have to consider VE, and second is the spacing. Where we calculate the spacing, the formula changes over there only. So I will quickly go to all the steps again. So once we calculate the equivalent shear, the next step in the shear design, calculate maximum allowable shear in concrete, that is VUC max. The formula is same, tau C max into BD. If this VUC max is greater than VUE, the section is okay. If it is not, if it is coming less than VU, then we need to redesign. Redesign means we need to resize the section. We need to increase the dimension of the section either, or we can change, or we need to change the grade of the concrete. Anything can be, anything is allowed. Okay. The next step is we have to calculate the shear force resisted by concrete, VUC. The formula is same, tau C into BD. Then we have to calculate the shear resisted by shear reinforcement, VUS, which is equal to VUE minus VUC. That is the total shear, equivalent shear, minus the shear resisted by the concrete. Then the next step, we have to calculate the shear, which is resisted by the minimum shear reinforcement. The formula is VUSV minimum equal to 0.4 BD. Then we calculate the shear force resisted by bent up bars, VUSB. The formula is same. And then we check the total shear force resisted by all these three provisions, that is the shear force resisted by concrete, shear force resisted by minimum shear reinforcement, and shear force resisted by bent up bars, combined, if that combined effect is greater than the total shear force acting on a beam, then we need to provide only the minimum shear reinforcement. If not, then we need to design the shear reinforcement, which is calculated by this. So there is one little correction. This should be VUE, okay, because we are considering now the equivalent shear force. Okay. So the design shear reinforcement is calculated for VUSV, which is given as VUS minus VUSV. Same steps are there, only where there is a change is in this formula. That is for calculating the spacing of the stirrups. If you remember the spacing for the stirrups, whatever we have used for the earlier design for shear, can anybody tell me what is the formula of SV we have used there?
0.87 Fy of stirrups into area of stirrups into D divided by VUSV.
VUSV, okay. So instead of VUSV, now the formula changes here, and instead of VUSV, we have to consider the combined effect of torsion and shear force here. Okay. So this formula is again given in IS 456, which is given over here. So if you consider this formula, which is given in clause number 41.4.3, in this formula, we want to find out SV. So the same formula we can rewrite as by putting SV on left hand side and moving ASV to the right hand side. Okay, so when we simplify this term, see here 0.87 Fy, we will move above, so I will shift all this term to this side. So 0.87 Fy into ASV upon TU upon B1 plus 0.87 Fy upon Vu upon 2.5 D1. So simply what the same equation I'm rewriting in terms of SV equal to. Okay, so you can do it. You can solve this, simplify this particular equation on paper. So when you rewrite the same equation by considering SV on the left hand side of the equation, we will get this expression. Okay, so by making use of this expression, we can find out what is the spacing between the stirrups. Now, if you remember, there are two criteria to decide the spacing between the stirrups, that the spacing should be less than 0.75 D or 300 mm, whichever is less. Now, along with these, there are two more criteria given when we consider the effect of torsion. Okay, what are those criteria? It should be also less than x1, and it should be also less than x1 plus y1 divided by 4. Okay, out of these four criteria, whichever is the lesser, that value we have to select. With respect to that value, SV should be less. Okay, now what is x1, what is x1 plus y1, those are given here. So instead of considering the formula first, let me explain through the diagram. X1 is actually the shortest distance between the stirrups. Okay, so these are the stirrups which are shown in blue color over here. So the shortest distance is in horizontal direction and the longest distance is in vertical direction. So x1 is the shortest distance and y1 is the longest distance. So simply I want to find out the distance between this one leg of the stirrup and second leg of the stirrup. This is x1. Similarly, the top leg and the bottom leg of the stirrups, when I calculate the distance between these two, it is called as y1. Okay, so this is x1 and y1. Now, how to represent the same in the mathematical format? It is given over here. X1 is b minus 2c1 plus phi s, where phi is the diameter of the stirrups. So I will go back to the diagram. B is the total width of the beam. B minus C1. C1 is the side cover. So 2C1 cover from both the sides plus C1 is actually the cover, the distance of the side cover is given from the center of the longitudinal bar. So this is, not center, from the side of the bar. So from this point up to this is C1. Okay, now I want the distance between the stirrups. So I have to consider the diameter of the stirrups also. That's why phi s is added. Okay, and this is the center to center distance. So phi s by 2 from one side and phi s by 2 from another side, it gives me total phi s1. So this is given as b minus 2c1 plus phi s. Okay. Similarly, y1 is again center to center distance between top and bottom stirrup. So again, this is the total depth, uh, capital D. So either capital D minus the 2 times D dash. Now again, the D dash is considered at the center of the longitudinal reinforcement. So instead of considering that, it is simply calculated like this, that D1 plus phi plus phi s. So this is D1. D1 is the center to center distance between the top and bottom reinforcement. Okay. So this distance plus half the reinforcement diameter from top and bottom. So it is half phi plus half phi. Combinedly it will be phi. And similarly, half of phi s. Phi s is the diameter of the stirrup from top and bottom. So combinedly it will be phi s. So this is the equation, D1 plus phi plus phi s. In short, I want the center to center distance between the two legs of stirrups as x1 and the center to center distance between top and bottom leg of the stirrup, which is y1. Okay, in any way you can calculate. This is the simplest way of representing x1 and y1 in mathematical format. So I have written in this fashion. Okay, so this is about the spacing between the stirrups. Now this clause is also given in IS 456, which is on page number 48, clause 26.5.1.7. So let me move to that clause. I will go to page number, see here, 48. Okay, page number 48, and it is given here, distribution of torsion reinforcement, clause 26.5.1.7. Okay, what it says, when a member is designed for torsion, torsion reinforcement shall be provided as, the torsion reinforcement for torsion shall be rectangular closed stirrups placed perpendicular to the axis of the member. The spacing of the stirrup shall not exceed the least of x1, x1 plus y1 by 4 and 300 mm, where x1 and y1 are respectively the short and long dimensions of the stirrup. Okay, so this is the short and long dimension of the stirrup. This is the criteria for distribution of torsion reinforcement. Okay, now after this, you can see here in this diagram, these are the main reinforcement, which is in tension side. Then this is the another reinforcement, which I will call as a main reinforcement only if we are considering ME2 effect, which is on the compression side. The blue line represents the stirrups, and two more dots you can observe here. These are again provided to take care about the torsion only, effect of torsion only. These are called as the face reinforcement or side face reinforcement, which are provided along the side face of the beam to take care of or to avoid the diagonal cracking, which may get developed in the beam due to torsional effect. Okay, so this side face reinforcement is calculated further like this. If the overall depth of the beam D is greater than 450 mm, additional longitudinal bars as side face reinforcement is to be provided. Now, how it is calculated? Its area is calculated like this. ASFR means area of the side face reinforcement equal to 0.1% of BD. BD is the overall cross-sectional area of the beam. Okay, so area of the side face reinforcement on each face will be ASFR upon 2. Okay, so this is the formula, and this formula is again given on page number 48 of IS code. So which is this one, this formula. Okay, I will say formula means the expression or the explanation given. Longitudinal reinforcement shall be placed as close as is practicable to the corners of the cross section, and in all cases there shall be at least one longitudinal bar in each corner of the ties. When the cross-section dimension of the member exceeds 450 mm, additional longitudinal bar shall be provided to satisfy the requirements of minimum reinforcement and spacing given in 26.5.1.3. Okay, so this is nothing but the additional reinforcement. 26.5.1.3. Let me check that. What is 26.5.1.3? This is side reinforcement. Okay, So where the depth of the web in a beam exceeds 750 mm, the side face reinforcement shall be provided along the two faces. The total area of such reinforcement shall be not less than 0.1% of the web area and shall be distributed equally on two faces at a spacing not exceeding 300 mm or web thickness, whichever is less. Okay, so this particular diagram shows the side reinforcement. This is nothing but our side reinforcement which is provided, and the spacing between these two should not be less than 300 mm, less than or greater than what is given. I think it is greater than. Shall not exceed 300 mm or web thickness, whichever is less. Okay, so the spacing between these should not be more than 300 mm or web thickness, whichever is less. Okay, is it clear, guys? The design for torsion. Any doubts in this? Students?
Yes, ma'am.
And the area of side face reinforcement by 2 का क्या लेते?
This is the total area. If you consider the ASFR is nothing but the area of these 4 bars. So we have to provide the side reinforcement equally on both the sides of the beam. That's why it is divided into half. 2 on this side, 2 on that side. Okay, so this is the total area of the reinforcement of the side face reinforcement. This is total. So we have to place it equally on both the sides. That's why it is made half. And this total area is to be provided on one face and the remaining on the another face.
And
Is it clear?
while providing this reinforcement, if our beam will become over reinforced, then
no, it will not become over reinforcement because we are designing it to take care about the torsional reinforcement. See, over reinforced beam, when we say, when do we call it as over reinforced beam? When this tension reinforcement is more than the or the area of the steel on tension side is more than the steel required for balance section. That is the definition of over reinforced beam. So whatever is the steel we provide on the tension side, that is only considered to check whether the beam is over reinforced or under reinforced. This is specifically a side reinforcement. It is not on the tension side or not even on the compression side. It is along the sides. Okay. So these side reinforcements are provided specially to take care of torsion. When there is no torsion on the beam, we do not provide these reinforcements. Is it clear?
yes, ma'am.
Okay, actually, I wanted to start one numerical example also, but the time remaining is just 10 minutes, and you have the practical also further at 3:30. So I need to stop the lecture today here itself. We will see the numerical example in the next lecture. There will be 2-3 types of examples which may be asked on the concept of torsion. One is the details of the beams are given, as you can see on the screen right now, that all the dimensions of the beams are already given. We need to only design we only need to find out what is the required area of the steel. Second is designing the entire beam for the given values of moment, that is bending moment, torsional moment, and shear force. So in that case, only these 3 values will be available to you, and all other you have to decide, okay, along with the material. So that normally that will be the case when you start designing your own plan, which you have developed for term work. Okay, so these 2 types of the problems, numerical examples, we will see in the next lecture. Now, time to give the attendance. So I will give you the link into the chat box. I request everybody.
And please upload this PPTs today only, no? So we can refer it before studying the numerical.
Yes, definitely. All other 2 lecture, remaining 2 lectures videos and this particular video